Hi everyone, this is Noah again. I'm going to run through a tutorial that is intended to be supportive of the things that I asked you to do on Lab 3 and the things that we asked you to do for the homework that's due this Monday. So in this tutorial, we are going to engage with the NOAA trial data, which is what we engaged with in Lab 3. And as usual, I've created a new folder for running and writing this tutorial. I have this folder called Lab 3 that I'm going to work on. The first thing that I might want to do is when I'm going to set my working directory shortly, so I might want to first try to copy the path name to this folder. And in that folder, if we peek back, we see that I have the neoadjuvant Herceptin trial data for me to work with. Excellent. So I'm now going to open in Applications, RStudio. Let's open it. Oop, I already had one open. Let's close all these windows. And we're going to remove everything from our working directory. We are going to open a new RScript file, and I'm going to just clear out this window. Great, so we have a new RScript file that we are going to use to engage with the NOAA trial data. So the first thing we're going to do is save this RScript. We are going to save it in this folder that we were just engaging with. So that folder was in Documents, PHI 512, Lab 3, and I'm going to call this Lab 3 Tutorial. Great, so I have saved it in there. The first thing I want to have in here is setting my working directory to that folder. So I have set WD, and then I copy paste that folder in. Remember, I copied the path name from before. The next thing I'm going to have in here is I'm going to load the tidyverse package or library so that I can use those piping operators. And the final thing is I'm going to read in the data. So read.csv, and then I have noaa.csv. As we recall, if we look back, is the name of the data file in there. Excellent, and I'm going to assign that data set once I read it in to this object named dat. Great, so I have these 3 lines. I'm going to run all 3 of them, and now I have a data object named dat, which in this case has 9 variables. Yours may have 10, or maybe I will have updated the data object by the time we next talk. All right. So there were a number of questions that I asked you to engage with in the lab. I'm not going to answer those exact questions. I'm going to answer slightly different questions. So we were engaging with the HER2 status of patients and their cancers. So again, some cancers are HER2 positive, some cancers are HER2 negative. Here, instead of engaging with HER2 status, we are going to engage with estrogen receptor status. This is another receptor that can live on the surface of a tumor. And often the quantity of this receptor that we find on the surface of a tumor determines maybe how the cancer grows. So some cancers are characterized as estrogen receptor positive. They have a lot of that receptor, an overexpression of that receptor, and some are estrogen receptor negative. So in this data set, let's look at the names of the data set for a moment. And we see there is this column called ER. That is the column that refers to the estrogen receptor status. So we could say dat $ER if we wanted to look at that. And we see some patients' cancers are ER negative, some patients' cancers are ER positive. Great. So the next thing we might want to do, let's imagine we are interested among those who receive standard of care therapy. We might want to look at the proportion that are ER positive versus ER negative. So of those on standard of care, what proportion are ER negative versus ER positive? So this is related to a question we engaged with in the lab. So how would we do this? So the first thing we want to do is only look at those on standard of care therapy. So we take our data set and we use this filter command to filter out and look at only those with the treatment variable equal to 0. Great. So I could run this command and it would give me a subset of my data. So if I run it, it gives me a subset. It gives me 92 people. And those are the people who receive standard of care therapy, 92 of our 152. And it just spit those out to the screen. I could assign that to a new object if I wanted to hold on to that, but I'm going to try to do things sort of all at once. So of these, of these 92 patients, or from these 92 patients, I would like to grab out the column that corresponds to the ER, estrogen receptor status. The name of that column was ER, and as you'll recall, we can pipe this into a command called pull that accepts a single column name. Great. So if I run this, now what I see is I see the ER variable corresponding to those 92 people. Now, the next thing we could do is we could take this and we could put it into the table command, which will tell me the number of these that are ER positive, ER plus, and the number that are ER minus. So we can further pipe this into table, run it again. We see 56 are ER minus and 36 are ER plus. And then we can finally pipe that into prop.table. And table and prop.table, you might remember from earlier videos and earlier labs, table expects as input a vector and outputs the number of each category in the vector. So it needs to be a vector of categorical variables, or a factor, as it's called in R. And then prop.table expects as input a table, and it transforms this into the proportions. So if we now run this, we see we get the proportion of patients who are ER negative versus the proportion of patients who are ER positive. Among those on the standard of care arm, among those with treatment equals 0. So again, we did all of this in one line. If we had wanted to, we could have maybe done this in 2 lines. I think other people engaged in another way where they said, okay, let's just take this first part where we filter out and grab only the patients on standard of care, and let's call this object something. Some people were calling it SOC. Oops. So if we run this line, it'll create a new object called SOC that only has those patients with treatment equal to 0. Okay, so we can run this. We have a new object. And then on that object, we can look at the ER column. We could use piping with the pull variable, or we could just say SOC $ER, right? ER is one of the column names here. And if we run this, we get to see that column, right? This should look like what we got before. And then we could use table and prop table here. We could say, okay, we could look at the table of SOC $ER. Again, looks similar. And then we could look at the prop table of the table of SOC $ER. So the combination of these 2 lines does the same thing as this line. I like line 9 because it says take data, or DAT, which is our data object, filter it in this way, pull out that single column, put this into a table, and then convert that into a prop table. It's a little easier to read than doing this with these intermediate steps. All right, for now, we're not going to engage with the PCR outcome variable. I want to leave a little bit of work for you all. So instead, we are going to look at another variable called ECOG. So this ECOG variable ranges, or could range from 0 to 5, and it indicates basically the state of the patient when they enter the trial. 0 meaning the patient is like fully active and good to go, 5 meaning the patient is actually dead. And so again, 1, 2, 3, and 4 indicate decreased levels of physical ability, decreased due to cancer and progression of cancer. So we have this variable ECOG. Let's look at that variable, dat $ECOG. And what we see is in this data set, it's either a 0 or a 1, right? So for everyone in the data set, their ECOG level is either 0, fully able, or 1, slightly decreased ability due to cancer. Or not necessarily due to cancer, just slightly decreased health, essentially. So let's imagine here, what I am interested in is the overall proportion, say, of people who have ECOG equal to 1. And so to look at that, there are a number of ways to do that. One way is I could just take the mean of this. The mean of a binary vector of 0s and 1s is the proportion equal to 1. And here I see roughly 8% of those are equal to 1. Let's imagine now I was interested in just the proportion of patients with ECOG equal to 1 on the control arm. So what is the prop of patients with ECOG equals 1 on standard of care arm? So how would I do this? Again, I want to take my data and I want to filter so that I only look at those patients on standard of care. Great. And then I want to use the summarize command to calculate this summary. So here I can say summarize prop ecog1 equals mean ecog. So let's look at this to understand what's going on. I take the data, I subset it, and I could have just used SOC here, but let's imagine we hadn't calculated that yet. Then on that subset of the data, I want to summarize it. And how do I want to summarize it? I want to look at that ecog variable or column, and I want to look at the proportion of ones, right? And that's what this is saying. And then I'm giving that a name. I'm calling that prop.ecog.1. Great, so if I run this line, what do I get out? It says, of those with treatment equals 0, here's the proportion that have ecog equal to 1. So it's roughly 10%, closer to 11% here. Great. So let's imagine I wanted to do the same thing. I was only interested in those with treatment equals 0, but I want to stratify now by ER status. So for those on standard of care with ER negative, what prop of patients have ecog equal 1? Similarly with ER positive. So again, on standard of care with ER negative status, what proportion have ecog 1? Similarly, for those patients on standard of care with ER positive, what proportion of patients have ecog equal to 1? So again, this is similar to a question that I wanted us to engage with during lab. So we could actually do this with multiple filter commands if we want, or we could do this with a filter command and a group by command. So let's try to do this with a filter command and a group by command. So again, I only want to look at patients with treatment equals 0. So again, I take my data and I'm going to filter and only look at patients with treatment equals 0. Then I want to do the same thing for patients with ER minus and patients with ER status ER plus. So I want to now group by and split my data essentially into two separate groups, one with ER status of ER minus and the other with ER status of ER plus. So I say group by ER. And then I want to calculate the same summary that I just did. So again, I could even copy paste this down. Oops. And here it's extended past this line. So it's okay, rather than keeping this all on one line, after each of the pipe commands, I can hit enter if I want to. And R knows when it's trying to run line 20 that, oop, it got to the end of the line and it needs to continue on to line 21. And oop, it got to the end of line 21 and it needs to continue on to line 22. It only knows this because the line ends with a pipe. Great, so if I run this now, what do I see? I see something like before, except now, instead of just looking at the overall proportion of patients with ecog equal to 1 on the control arm, it does this separately for the patients who have estrogen receptor negative tumors and the patients who have estrogen receptor positive tumors. Perfect. So again, I was able to do both of those at once. If I didn't want to be so sneaky about it, I could have used the filter command in the following way. I could have said, okay, let's filter such that treatment is equal to 0, and let's also filter such that ER is equal to ER minus. And one thing to note here, ER minus has to be in quotes, because I'm trying to say ER, I want it to equal this exact set of characters. And when you're trying to specify an exact set of characters like this, again, you need quotes around it. So if I did this, and then I added this summarize command, oops, and then, again, I'm going to do this on multiple lines again just to make life a little bit easier. So this filters out so that we only look at people on standard of care. It again filters out so that we only look at people with ER negative tumors, and then it summarizes the proportion that have ecog equal to 1. Right, and we see here 10.7% have ecog equal to 1 among those with ER negative tumors, and that agrees with what we got with group by. And we could similarly switch this to ER positive if we want. One last thing to note, I did this in two different commands. If I had wanted to, or sorry, two different filter statements, I ran filter this and then filter this other thing, we can actually put multiple conditions into filter at once. So for example, if I put a comma in here and I add in this after the comma, this filter command will now filter and only pick people with the following two conditions true. The first is that their treatment should be equal to 0. The second is that their ER should be equal to this set of characters ER minus, right? So I can run this, and then from here I can summarize, and it will give me the same result, only now I have only one filter command with two conditions rather than two filter commands. So again, you would probably do this once for ER minus and once for ER plus. Great. If instead you had a categorical level with a lot of different categories, then group by is going to be nicer rather than having to filter for each of the categories separately. Great. So let's now move on to that last question, the sampling distribution question, and we're going to think a little bit more about hypothesis testing maybe more generally here. So in the question that was asked on the lab, there was this friend of yours who said they claim that each person on the new treatment arm with HER2-positive breast cancer had a 30% chance of responding to treatment, and they wanted, or you wanted to verify if your data were consistent with that, and so you had to build a sort of a hypothesis test around that, identify what the null hypothesis was here, the alternative, generate a sampling distribution, and find a p-value. So I'm going to leave that for you to do, and I'm going to change the problem a little bit. Let's imagine rather than 30%, suppose my friend says that each person has a 70% chance of responding to treatment. So again, I've changed 30% to 70%. What we want to do now is run a statistical test, a hypothesis test, to identify if this statement is consistent with what we saw in the data. So the first thing we might want to do is just look at the proportion of people in our data who respond to treatment and compare that to 70%. And again, of responding to, by treatment here, I mean of responding to trastuzumab plus standard of care, so that new exciting treatment. So in order to identify the proportion of people who respond to that treatment, we're going to take our data, we are going to filter. Now we're not interested in treatment equals 0, we want treatment equals 1. Right? And of those patients with treatment equals 1, we want to look at the proportion who have PCR equal to 1. And again, we could try to do more filtering and stuff, or we could say the mean of a binary vector is the proportion of 1s, that those are actually equivalent. And so we could use the summarize command and say response proportion equals mean of this variable PCR. Again, summarize does some calculation on columns of the data matrix or data object that's passed into it. And here the calculation we're doing is looking at the PCR column and calculating the mean. And we're going to call that resp.problem. So if we run this, we see in our data, 46% of people have responded. Roughly, the proportion is 0.46. Okay? So now the second question is, how many people actually are there in this data set, right? Because we're thinking about this in terms of flipping coins. So the next thing we want to do is we want to count the number of rows of people who had treatment equals 1, who got the new treatment. And so we can do that by, again, taking our data, filtering to only take observations with treatment equals 1, and then count the number of rows. So if we run this command, we see, okay, so there were 60 people on the new treatment arm. 46% of those people responded. And our friend is saying that actually each person had a 70% chance of responding. So 46% seems a lot lower than 70%. The question is, are we just seeing a much lower proportion due to random chance? Is it just that we got unlucky? Or would this have been so extreme that really we don't believe our friend that each person has a 70% chance of responding? So we've looked at the proportion of people who respond. Let's actually look at the number of people who respond. So there are a number of ways to do this, but we could do this with that filter command where we filter for multiple things. So let's filter out and identify those patients with treatment equals 1 and PCR equals 1. Right, and then let's count that number. Ooh. So again, we're using the fact that we can have two conditions in filter. So when we run this, we see, oh, there are 28 patients who responded on that arm. And if we looked at 28 divided by 60, we would see that it is exactly 0.4666, etc. Okay, excellent. So the next thing we have to do, we have to identify our null hypothesis and identify our alternative hypotheses. Here, the null hypothesis, the thing we are trying to check the veracity of and see if it's consistent with our data, is this statement our friend made. So the null hypothesis here is going to be each person has a 0.7 probability of response, right? And the alternative here, we're gonna engage with a two-sided alternative. HA is going to be each person has some other probability, some response probability that's not 0.7. So often we write this as pi equals 0.7. Again, here we're thinking of this as pi is some number that is not 0.7, has some other probability of response, not 0.7. Excellent. So now we need a sampling distribution for what the number of patients who responded would have looked like in this world that was imagined by our friend. So how do we do that? We want to take a coin that has a probability of heads of 70%, 0.7. We want to flip it 60 times and record the number of heads. And we want to do that run that experiment 1,000,000 times. So we say R binom. So the first number is the number of experiments we want to run. The second number is how many times we want to flip the coin per experiment. And the third number is the probability of heads we want for each flip. So if we run this, it's going to run a bunch of experiments, each one with this coin with a 70% probability of heads. And this is the number of heads that we're going to see. Excellent. So we don't just want this output to the screen, though. We want to store this vector so that we can use it later. I'm going to call it trials. So we run this line, we get 1,000,000 trials, and we can look at the histogram of these trials. So what do we see? We see these trials, generally in these trials, out of the 60 people, 40-some experience PCR, 40-some respond, and we only observe 28 in our data set, and 28 is pretty far into the tail of this distribution. Right? So now the first thing we want to do is we want to try to calculate a p-value. Right? And to calculate a p-value, what we need to do is we need to figure out what proportion of this histogram is less than 28, or really less than or equal to 28. So one way to do that, so again, trials is this really long vector of numbers, of counts from each of these trials. So we can look at trials and we can compare it to 28. So if we run this line, for each of those trials, it tells us were there greater than 28 people who responded or less than or equal to 28 people who responded. So true here says there were less than or equal to 28 people. False would say there were greater than 28 people. So again, this for each trial tells us if there were greater than or less than or equal to 28 people. And now I want to take this vector and I want to figure out what proportion are true, because that's exactly the proportion of this histogram that falls to the left of 28. So there are a number of ways to do it. I'm going to do two different ways. One, this is sort of a cheap trick. Trues and falses are actually coded in R as zeros and ones. So if I want the proportion of trues, I can look at the mean of a vector of trues and falses, and it will give me the proportion of trues. That's kind of sneaky, so let's not worry about remembering how to do that. The other thing we can do is we can use table and prop table, right? Prop.table tells us for categorical variables, or it doesn't have to be categorical, it can be these Boolean or binary variables, the proportion of observations that fall in each class. Here our two classes are trues and falses, and we might want to look at the proportion of these observations that are in the true class versus the false class. So we could say, we could name this an intermediate object if we want. We could call, I'm just going to call it intermediate because I want to use this later. So I'm going to run this line, and it will store then that vector of trues and falses. And then I would say prop.table of table of intermediate. And when I run that, it gives me exactly what I saw before, like a very small number of these are true, right? It's like 0.0001. So this is like 1 in 10,000. Between 1 and 2 in 10,000 of these trials in the world imagined by our friend will be less than or equal to 28. So again, it's incredibly rare then in a world where each patient has a 70% chance of responding that we would observe 28 or fewer responses. So if we were interested in a one-sided p-value, then our one-sided p-value would be exactly this number. If we were interested in a two-sided p-value, we would take this number and multiply it by 2. So for a two-sided p-value, we would look at this times 2, which would be 0.0003. So if we were running a hypothesis test, a two-sided hypothesis test at the 0.05 level, then that would tell us our p-value is much smaller than that. So we have plenty of evidence at the 0.05 level to reject the null hypothesis that each person has a 70% chance of responding to treatment. Right? Again, small p-value means the null hypothesis is likely not true. It means that there is strong evidence against the null hypothesis being true. Great. Now, one more thing I want us to cover, because this will be important for your homework, is critical values, right? So if we were running a level 0.05 test, we would want to find the critical values, the number of patients that we would have needed to see, either the cutoffs for number of patients we would have needed to see to declare significance at the 0.05 level. So again, refer to the course slides for, I think, lecture 8, if you were a little bit confused about what we mean by critical values. But again, we can imagine calculating a p-value if we'd observed 28 people, a p-value if we observed 29 people, a p-value if we'd observed 30 people responding, 31 people, etc., and finding the largest number of people such that our p-value was just below 0.05, and that's sort of the critical value, the number that we would have needed to see in order to, declare our friend's statement false. So we mentioned on the slides you can do this with the quantile function. And so here what we would do is we would look at this trials thing. And what we want is the 2.5th quantile and the 97.5th quantile of trials. So we run the quantile command. The first input is trials, oops. And the second input, let's remind ourselves, let's look at the help documentation. The second input that we want is called probs. So trials is the first input, or I guess, yeah. And the second input has a name called probs, and these are the value that you want to calculate the quantile at. So if I want the 2.5th quantile, or the 0.025 quantile, I would say probs equals 0.025. And if I want the 97.5th quantile, I would run the quantile command, only now probs would be 0.975. So again, if we go back to our histogram for a second, this says that if we look at the values 35 and the values 49, that only 2.5% of the histogram falls to the left of 35, and only 2.5% of the histogram falls to the right of 49. So these are now our critical values. We would reject our null hypothesis if in our trial we had observed either fewer, less than or equal to 35 patients, or greater than or equal to 49 patients responding to treatment. I think I said 49. I meant 49. And in our trial, we observed 28, which is less than or equal to 35. So that is in this region where we can say, we suspect the null hypothesis is incorrect. It is not consistent with the data we've observed, and thus we will reject the null hypothesis, in this case at the 5% level. And again, we also could have gotten that from the p-value. The p-value that we calculated, in this case it was 0.0001 for one-sided or 0.0003 for two-sided, is much less than 0.05. So we can reject the null hypothesis clearly at this 0.05 level. Great, so I hope this was helpful. I do think if this idea is confusing, right here we engage programmatically, but if the idea of what is going on with hypothesis testing is still confusing, which it is a complicated and subtle idea, I think spending a little bit more time going back and thinking about sampling distributions more generally and evaluating evidence and heuristically what we might be doing, and then mathematically why that makes sense, why that connects to that heuristic that we believe, would be a very good use of time.